Hello everyone, please allow me to introduce my group member first. Zhao, Connor, Junqing, and I. We are the team from 448, and the project topic we bring to you is composition of nonlinear amplifier for 6E APSK modulation. We know that in the service signal transmission application, like the space platform and satellite communication, they usually use the digital communication signal to send the data back to the ground, and the power amplifier can prove the signal with energy need for this process. The pre-compensation can use to compensate for abnormal case caused by the power amplifier. And in this project, we use MATLAB simulation to achieve the function of transmitter and receiver. Amplitude and phase shift key is a digital modulation scheme. The 16 APSK support to the DVB-S2 standard, and the constellation always be composed of two concentric rings of 4 and 12 PSK points. We assume the radius of inner ring is R1 and the radius of outer ring is R2. Then we can use the ratio of R2 over R1 to get the value of I and Q. As I mentioned earlier, one of the main traits of the development of receiver and other wireless devices is the use of digital signal processing to implement more and more receiver function. However, due to the limitation of the conversation process, some signal stage might still be remain. Then the compensation becomes necessary in this progress because the pre-compensation technique can also be used to suppress nonlinear distortion.
So this project began with a comprehensive literature review. We looked at DVB-S2 standard. It replaces DVB-S, which was the original standard. It offers several modes of modulation. We looked exclusively at 16 APSK. We also looked at nonlinear power amplifiers because we want to operate in the nonlinear region as it results in the greatest power efficiency. But operating in that region does bring with it the distortions AM to AM and AM to PM, which are amplitude modulation and phase modulation distortions. And in order to mitigate those effects, we researched precompensation or predistortion. So here's the project flow of our overall program in MATLAB. Within the transmitter, we have a random bit generator. Those bits are then modulated and passed through a root raised cosine filter. Then they're precompensated, as discussed before, although that's an area of future study. Then they're passed through the amplifier, at which point they're transmitted. Gaussian noise will be introduced to simulate noise from the physical environment. And then at that point, they're passed through another root raised cosine filter from the receiver. They can then be demodulated, and bits can be compared in order to determine the success rate. So over on the right here, you'll see two power curves. One shows AM to AM distortion, and the other shows AM to PM distortion. We want to operate in the region right about where the compression is labeled on the top figure and phase shift on the bottom figure. As mentioned, we operate in that region because it brings with it the greatest power efficiency. But the real problem is that it introduces these distortions, and phase shift in particular becomes a function of power, which is not at all ideal, and we want to mitigate those effects because, as you'll see on the next slide, it completely distorts the constellation diagram, and the results would be illegible to the receiver.
The ideal constellation we expect are the red dots in the first graph. However, in real life, data transmitted may not have the same amplitude and phases as we hope. The actual data may rotate it like the second diagram, which means the data has been distorted. Our solution approach is to use MATLAB generated function to get over the distortion and crack it into the ideal area we want in the following semester. We first generate a transmitter and a receiver model in MATLAB, which every communication system must have. Second, we add noise source to stimulate data transmission in the real world. Third, we use CREEGAN MMIC power amplifier in our stimulation. Enter the data of the amplifier from the datasheet into MATLAB. Wrote code to imitate the compression of the amplifier. Our results are not complete. We use MATLAB code to find out the bit error rate. A low error rate indicates our stimulation can communicate normally. This diagram shows the bit error rate with image by comparing the transmitted and received data before adding the amplifier into the model. The bit error rate is 0 here. After adding the amplifier, the bit error rate is more than 0, but we did not transfer the bit error rate with amplifier into a diagram yet.
Okay, now I'm going to talk about what we're gonna do next semester. So first of all, we're going to generate the spectrum plot, and then we'll finish the building of a distortion and precompensation model. And finally, we will determine the performance of the whole project. And here is our conclusion. First, we know that the MATLAB can be used to simulate the communication systems. And the operation in the PA nonlinear region could increase the power efficiency. And also the pre-distortion can compensate for nonlinear amplifiers. And we build the RRC shaping used for spectral containment. And according to our previous research, many satellite communication protocols use DVB-S2 standards nowadays with 16 APSK modulation. This is what we got so far. For more conclusion, we will provide them after finish our whole simulation and next semester. Now, is there any question?